Hey guys, we're going to be continuing our weather journey today and talking about winds, particularly global winds. Global winds are winds that travel for hundreds, if not thousands of miles across Earth's surface. They travel in predictable patterns and they travel persistently, meaning they are constantly blowing. It's not like walking outside and a gust of wind blows by and messes your hair up. Those are local winds and they're different. We're going to be talking about global winds that are constantly blowing and affecting our climate and our weather patterns. So, what you're looking at is a simulation of the global winds on Earth's surface. Particularly, we're looking at North America up here and South America down here. So, this space here to the right is the Atlantic Ocean. And you can see these winds that are traveling in curved paths. The darker the green means the more concentrated and more powerful the winds are. They may be even traveling faster. Same thing for up at the North Pole. You can see more concentrated green spaces, which means those winds are traveling and they're stronger and maybe even moving faster. We're going to be talking about why these winds are traveling in a curved path. If you already know it, you know this is the Coriolis effect, which is a result of the spinning of Earth. Earth spins, which causes things to appear to move in a curved path. So that affects our winds as well. This is a pretty cool website. I'll link it in the agenda. So later, once you're all done with your work, you can go back in and kind of play with it. You can add in the water currents in the ocean and see how they move around. You can also look at Earth from different perspectives. So you really see that dark green there towards the bottom and the top of the image. So once you're all done, you can always go back and play with it. It's pretty cool. All right, we are going to watch a video about the Coriolis effect. It's about 2.5 minutes long, and as you're watching it, you are going to be filling in your notes page for Coriolis effect. So definition, facts, examples, non-examples. Fill this in as you watch the video. If you feel that you missed something or the video goes too quickly, you can always come back and fill it in. Watch it again. I'll link it in the agenda. Here's the Coriolis effect.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placements of jets inside the toilet. But that's it, that's the Coriolis effect. If you liked this short and to the point video, give this video a like, and if you want to see more videos...
All right. Again, if you missed some of it or you need to go back, I'll link this in the agenda. You can always go back and fill in what you missed. All right, let's talk about our different types of winds. Remember, we're talking about global winds that travel for hundreds and thousands of miles across Earth's surface. They're traveling persistently, meaning it's not a gust. They are constantly moving, and they can be moving in predictable patterns. So first, we're going to label the direction of the winds from different latitudes, and then we'll identify what they are and add a couple interesting facts about them. So remember that wind always moves from low pressure to high pressure. So we're going to actually add that as a little extra note at the bottom. Wind, you should be filling this out as you watch and listen, always moves from high pressure to low pressure. So if we're starting here at the equator, and I'm going to label this equator, just EQ for equator, and we are at low pressure, then air is going to be flowing towards that equator from areas of high pressure. So wind leaving high pressure up here is going to head towards low pressure, but remember, because Earth is spinning, it's going to curve. And since the equator is having to move faster, it's going to fall behind. Same thing from this high pressure. This wind wants to move to low pressure, but it's going to curve and fall behind because it's coming from a slower movement or spin around the Earth. And then we have high pressure here. We're going to move towards low pressure, but we're going to move faster. So we're going to go forward or towards the east. High pressure to low pressure. High pressure to low pressure, but we're going to be moving ahead because we're moving from a faster zone to a slower zone. And then same thing from 60 degrees and 90 degrees. High pressure to low pressure, but we're moving towards the equator, so we fall behind. High pressure to low pressure, but we're moving towards the equator, so we fall behind. We head west. So that's how air in our global winds moves and curves, because Earth is spinning, but it's also trying to get from areas of low pressure to high pressure. All right, let's label some of these. So let's start with our latitudes, lines of latitude. So we have our equator. Sometimes that's called the doldrums. Forgot my L-D-O-L-D-R-U-M-S, doldrums. That's a sailing term for latitudes close to the equator. Here the winds are not really strong, so sailboats and anything wind powered would not move super quickly as it would in other latitudes. However, it is an area of low pressure, meaning that you're going to get a lot of cloud formation, you're going to get a lot of rain. So the doldrums, not great for sailing, but it causes a lot of rain and wet weather. The equator is where you get a lot of rainforest. Because of that cloud formation and eventual rain, you get a lot of rainforest there. All right, moving up to our 30-degree latitude. 30-degree latitude are often called the horse, as in the animal, latitude. There's one there, and then there's one down here. Horse latitude, there's a couple different theories about why they're called the horse latitudes. My favorite theory is that because these are areas that don't have a lot of wind, boats sailing from Europe would often take way longer than they anticipated sailing across the ocean. And so they would get to a point where they realize they're going to run out of food and water. And so they're going to try to relieve themselves of anything that's going to be using a whole lot of food and water, like livestock, including horses. So one theory is that this is where boats would encounter very little wind, so they would kind of stall out in the ocean, and they would have to get rid of some of their livestock so they can conserve their water and food. So the horses would essentially go for a forever swim in the ocean, and they would send the horses overboard so they could keep the water for all their crew. All right, and then moving up to the 60-degree latitude mark. This one doesn't have a fun name, so we're just gonna leave him be. So the winds that are moving from our horse latitudes up to our equator and down from the horse latitudes towards our equator, these are called the trade winds. Notice they're moving from east to west. This was hugely impactful during the Age of Exploration because these were the winds that the sailors and the traders used to move across the ocean. And they would move into the Caribbean, come to the Americas from Europe and from Africa. And then in the Pacific Ocean, you would see similar movements. So these are called the trade winds, both above and below the equator. So between 30 and 60 degrees, you had trade winds. And then between 30 and 60 degrees, between 0 and 30 were the trade winds. Between 30 and 60, both north and south, we had westerly winds. They're moving from the west to the east. So these are called the westerlies. And then along your 30-degree latitudes, these are areas that are really dry. Remember, high pressure brings dry, sunny weather. So this is where we expect to see a lot of deserts. And I know our map is getting crowded, but here's Northern Africa where there's a large desert. Here is the southern United States, which has a lot of deserts in Arizona and New Mexico, Southern California, Western Texas, lots of desert. Same thing down here, the Atacama Desert in southern South Africa or South America. And then you do have some desert space down in the southern tip of Africa as well. So these are where you find a lot of the world's deserts. All right, our polar winds coming up from the poles, and they are going east to west. These are called the polar easterlies, both north and south. The 60-degree low pressure, remember, brings rain. 60-degree latitudes is where you find a lot of forests. Now, this 60-degree is mostly ocean, so there's not a lot of forest there, but up here in northern Canada, you're going to find lots of forest. They get lots of rain up there. And trees like a lot of cool temperatures, so that is perfect conditions for them. All right, we've included a lot. Let's just recap our 3 kinds of global winds. So we had our polar easterlies, these go from east to west, and they are dry and cold. Then we have our westerlies. These go from the west to the east. And our westerlies are responsible for North American weather. Those are the kinds of winds that impact us in North America, the United States, the most. And then we had trade winds. Those sometimes are called the tropical easterlies, so they go east to west, and they are the source of most storms. Most of our tropical storms, like hurricanes, are because of trade winds. All right, and then we're going to color code just to make it a little bit more clear. So let's highlight. And I'm going to use red for my trade winds because they're close to the equator. They're in the tropics where it's warm. So we'll color these the trade winds. Make them red because they're closer to the equator. There we go. And then I'm going to switch to purple for our westerlies. They are between our horse latitudes and 60 degrees. Those poor horses. And then we'll switch to blue for cold, our polar easterlies. They are up here at the poles. There we go. All right, polar easterlies, westerlies, trade winds. Those are our three main global wind patterns. And we know that wind always moves from high pressure to low pressure. That's it for this page of your notes. Have a good rest of your day.